Here a function f is continuous on closed and bounded interval AB, and x1, x2, x3, xn all belong to this interval AB. We have to prove that a point C belongs to the open interval AB such that fc equal to the mean of fx1, fx2 dot fxn, that is fc equal to the arithmetic mean of fx1, fx2, fxn. We have to prove this, and here the condition is f is continuous on this closed and bounded interval AB, where x1, x2, x3 dot xn all belong to this interval, that is bounded interval AB, closed and bounded interval AB. We have to prove that there exists a point C belongs to this open interval AB such that fc is equal to the arithmetic mean of fx1, fx2, fxn. Now let's start the solution. Here f is continuous on the closed and bounded interval AB. F is continuous in closed and bounded interval AB, and here the points are taken as x1, x2, x3 dot xn all belong to this interval. x1, x2, xn all belong to this closed and bounded interval AB, closed and bounded interval AB. Now we have already known some theorems on the continuity of a function on a bounded and closed interval. Here we shall apply these theorems for the sake of the solution of this problem. Now at first we take the theorem from continuity of a function. The theorem is if theorem 1 is if f is continuous on closed and bounded interval, then f is bounded. It has two bounds a supremum and an infimum. Supremum means least upper bound of the upper bounds, least of the upper bounds, least bounds of this among these upper bounds of this function, and infimum is greatest lower bound, the greatest bound in the among the lower bound of this function, greatest lower bound. Infimum is greatest lower bound, that is greatest lower bound. Supremum is least upper bound, least among the upper bounds, and infimum is the greatest among the lower bound of this function. And also function f attains these bounds at certain values of x belongs to the closed interval AB, that is fc equal to supremum considered as capital M, and C belongs to the closed interval AB, and FD equal to infimum where also D belongs to closed interval AB. So FC not equal to FD, FC not equal to FD. Here FC is the supremum, that is least upper bound of this function in this closed interval, and FD is the infimum, that is greatest lower bound of this function in this interval. These are two bounds of this function in this interval. So all values, other values of these functions all lie between these two bounds, that is fx1, all other values, that is at the value x of x at x1, x2, x3, xn, functional value fx1. So fx1, fx2 dot fxn, these values lie between these two bounds, that is less equal to fc and greater equal to fd, because these are two bounds of this function in this closed and bounded interval AB. These are the two bounds of this function. Here fc is the least upper bound and fd is the greatest lower bound. So all values of f in this interval AB also lie between these two bounds, that is fc and fd. So we can write this, and so fx1 less equal to fc greater equal to fd, fx2 less equal to fc greater equal to fd, dot dot fd less equal to fx n less equal to fc. This. So we can write, if we sum up these inequalities, we get nfd less equal to fx1 dot dot fxn less equal to nfc. We take summation of this inequality. We have taken summation of this inequality, and this summation is this, that is nfd less equal to fx1 plus fx2 dot dot fxn less equal to nfc. So this is also written as fd less equal to fc, that is fd less equal to the arithmetic mean of fx1, fx2 dot fxn less equal to fc. fd less equal to arithmetic mean less equal to fc. Now we can apply the other theorem, that is which is already known to us. This theorem is intermediate value theorem of the function on continuity of the function f. Here we can apply the intermediate value theorem value theorem for the solution of this problem. This intermediate theorem is the intermediate theorem of the function on the continuity of the function. This theorem is well known to us. This theorem is if f, intermediate value theorem is if f is continuous on the closed and bound interval AB, and also FA not equal to FB, then there exists P belongs to the open interval AB such that Fp equal to mu always belongs to the supremum, that is least upper bound and greatest lower bound, that is this is infimum, this is supremum. This is so f attains every value between these two bounds. So the function attains every value between these two bounds, that is one is greatest lower bound infimum and other is least upper bound, that is supremum. F, that is function attains every value between these two bounds, that is infimum and supremum. Now, so we can apply this theorem here. Here we have already got fd less equal to fx1 fx2 dot fxn less over n less equal to fc. This is a intermediate value. This is an intermediate value in the interval FDFC, in the closed interval FDFC. This is an intermediate value. This value lies between these two bounds. One is FD and other is FC. FD is infimum, FC is supremum, and this is an intermediate value. And this intermediate value is attained by this function. From this theorem, we can say this value, this intermediate value is attained by this function in this interval, and this value suppose fp. So by this theorem, by intermediate value theorem, we can say fp equal to dot over n. This is an intermediate value of the function between these two bounds fd and fc, and this intermediate value must be attained by this function in this interval. This is the intermediate value theorem. So we have got fp equal to this, that is fx1 plus fx2 plus fxn over n, which is the arithmetic mean of fx1 fx2 dot fxn. Here p belongs to the open interval AB. By this theorem is intermediate value theorem. theorem. Thus we have got the result here.